In 1937, no carrier-based fighter on Earth could match a land-based opponent. The physics made it impossible. A carrier fighter had to be light enough to launch from a ship, strong enough to survive the shock of an arrested landing, and compact enough to fold its wings and descend into the hangar deck below. Every one of those requirements added weight or subtracted power. The result, everywhere in the world, was a compromise. Carrier fighters were slower than land-based fighters. They climbed worse. They turned wider. They carried less fuel. Every navy that operated aircraft carriers accepted this as a law of nature. The Americans accepted it. The British accepted it. The Japanese did not. In October 1937, the Imperial Japanese Navy issued a specification so extreme that one of the two companies invited to bid walked away from the table. The specification demanded a carrier fighter that could outrun, outclimb, and outmaneuver every land-based fighter in the world while carrying two 20mm cannon, two 7.7mm machine guns, a full radio set, a direction finder for navigation, and enough fuel to fly for 6 to 8 hours at economical cruising speed. 8 hours. A round trip of over 1,500 meters from a ship in the middle of the Pacific to a target and back. No fighter on Earth had that range. No carrier fighter came close to that speed. The wingspan had to stay under 12 meters so the aircraft could fit on a carrier elevator. The Navy wanted the fighter to climb to 3,000 meters in 3.5 minutes. It wanted a maximum speed of 500 kilometers per hour. It wanted maneuverability equal to or better than the A-5M, the fighter it was replacing, which was already the most agile carrier aircraft in the world. The men who wrote the specification were not engineers. They were naval officers who had watched their pilots fight over China and concluded that the next war would be fought across distances so vast that a short-range fighter was useless regardless of how fast it flew. They wanted a machine that violated the known limits of aircraft design. They sent the specification to Nakajima and to Mitsubishi. Nakajima's engineers studied the numbers, concluded they were physically impossible, and withdrew from the competition in January 1938. At Mitsubishi, one engineer looked at the same numbers and saw a way through. His name was Jiro Horikoshi. He was 34 years old. The company he worked for was not a small workshop. Mitsubishi was an empire. Yataro Iwasaki, a former samurai from Tosa province, had founded it in 1870 as a shipping company. He had leveraged government contracts, strategic ruthlessness, and the chaos of the Meiji Restoration to build a conglomerate that touched every sector of the Japanese economy. By the 1930s, the Mitsubishi Zaibatsu was one of the 4 largest industrial groups in Japan, alongside Mitsui, Sumitomo, and Yasuda. It built ships, it mined coal, it manufactured steel, glass, paper, and electrical equipment. It ran banks, insurance companies, and trading houses. It owned real estate across Tokyo, and it built airplanes. In 1920, Mitsubishi had established the Mitsubishi Internal Combustion Engine Company to manufacture aircraft engines. That company became Mitsubishi Aircraft in 1928. In 1934, Mitsubishi Aircraft merged with Mitsubishi Shipbuilding to form Mitsubishi Heavy Industries, which by the late 1930s was the largest private company in Japan. Its aircraft division operated out of the Nagoya Works, a sprawling manufacturing complex in central Honshu. The Nagoya plant built bombers for the Navy and fighters for the Army. It employed thousands of engineers and assemblers. The infrastructure was vast. The engineering talent was deep. The resources were real, but no amount of infrastructure could change the physics. The specification the Navy had written demanded a machine that should not have been possible. Horikoshi's job was to make it possible. Anyway, Jiro Horikoshi was born on June 22, 1903, near the city of Fujioka in GMA Prefecture, northeast of Tokyo. He grew up watching airplanes transition from curiosity to strategic necessity. By the time he reached university, the future of national power was being written in the sky. He enrolled at the University of Tokyo and graduated in 1927 from the newly established aviation laboratory within the engineering department. One of the first cohorts trained specifically for aircraft design. He joined Mitsubishi immediately and began his career at the Nagoya Works. His first project was the one MF-10, an experimental carrier fighter that never passed the prototype stage. It flew. It did not fly well. The landing gear was weak. The handling was poor. The project failed. But Hiroshi learned from the failure the way all serious engineers learn from failure. Not as a setback, but as data. The lessons fed directly into his next design. In the mid-1930s, Horikoshi led the development of the A-5M, a carrier fighter he designed from the ground up. The A-5M was a clean, low-winged monoplane with fixed landing gear and an open cockpit. It was light, fast, and extraordinarily maneuverable. It entered service with the Imperial Japanese Navy and immediately proved itself over China during the Second Sino-Japanese War. Japanese pilots flying the A-5M against Chinese Air Force fighters, many of them Soviet-built, reported decisive advantages in speed and agility. The A-5M could outturn anything it faced. It established Horikoshi's reputation as the foremost fighter designer in Japan. When the 12-sheet specification arrived in 1937, the Navy didn't wonder who should lead the project, but Mitsubishi's management hesitated. The company was already occupied with a Navy bomber contract. The executives considered rejecting the fighter specification entirely. They had the A-5M in production. They had bomber orders to fill. Taking on an impossible specification for a fighter that might never work was a risk the business side was not eager to accept. Hiroshi pressed hard. He argued that his team could meet the performance demands if they were allowed to pursue an extreme weight reduction strategy. He argued that the fighter contract was more important than the bomber. The Navy agreed the bomber project was shelved. Horikoshi was given the design team and the resources. His engineers went to work in the Nagoya plant. The project that Nakajima had declared impossible was now the responsibility of one man and his team. The central problem was weight. Every requirement in the specification demanded performance that only a lighter aircraft could deliver. More range meant more fuel, which added weight. More armament meant heavier guns and ammunition, which added weight. The heavier the aircraft became, the more powerful the engine needed to be, and more powerful engines were heavier. The spiral was vicious and self-reinforcing. The only way to break it was to remove weight from every other part of the airplane. With a discipline that bordered on obsession, Hiroshi understood this immediately. He also understood the price. He made a decision that would define both the triumph and the tragedy of the machine he was about to create. He stripped the aircraft of protective armor. No steel plate behind the pilot's seat. No protection around the fuel tanks. No self-sealing bladders to close bullet holes and prevent fuel leaks. Every Western fighter under development in the late 1930s was adding these survivability features. The Americans were adding them. The British were adding them. The Germans were adding them. Horikoshi removed them before they were ever installed. The reasoning was precise. Japanese aero engines in the late 1930s produced 20 to 30% less power than their American and European equivalents. Auer himself acknowledged this gap. The only way to match or exceed Westerner performance with an inferior engine was to build an airframe so light that the engine's disadvantage became irrelevant. He used a new aluminum alloy called Extra Super Durair Alamin, designated T7178. It was stronger than standard aircraft aluminum, which allowed thinner structural members, which saved weight at every joint, rib and spar throughout the airframe. The wings were built using a single continuous spar design with integral fuel tanks built into the wing structure. The fuselage was assembled in two major sections, joined by a ring of 80 bolts. Engine, cockpit and wing formed one rigid unit. The tail section formed the other two pieces. The construction method was revolutionary. It simplified manufacturing and saved weight simultaneously. The result was an aircraft with an empty weight of approximately 3.74 pounds. The Grumman F-4F Wildcat, the American carrier fighter it would face in combat, weighed 5,758 pounds empty. The Zero was nearly a ton lighter than its primary adversary. That gap was not an accident. It was Horikoshi's answer. On April 1, 1939, the first prototype lifted off the runway at Kagamiyara Airfield near Nagoya. The test pilot was Katsuzo Shima. Oroshi watched from the ground. The aircraft climbed fast. It turned tight. The controls were responsive and balanced at every speed. Flight testing continued through the spring and summer. A second prototype was built with the more powerful Nakajima Sakai 12 engine, a 14-cylinder radial producing 940 horsepower. The performance numbers with the new engine were extraordinary. Maximum speed reached 331 miles per hour at 15,000 feet. The aircraft could climb to 9,800 feet in 3 minutes and 30 seconds, meeting the Navy's most demanding requirement almost exactly. Its range with an external drop tank exceeded 1,600 meters. No carrier-based fighter anywhere in the world approached those numbers. No land-based fighter matched the combination of range, speed, and agility. The Navy accepted the aircraft for service in July 1940, the Japanese year 2600,